All right. Good morning, everybody. Here we are back again. Um, Today we are finishing up the exercises that we didn't do yesterday in 4.1, starting 4.2, and today we have a double session. So we're going to start with this stuff. We can probably get past this stuff if I had to guess. But yeah. Um, I'll start with a theorem, um, which is that let P be a prime ideal of A. There exists an isomorphism from the localization at P in spec A of the M module to just the localization of M at P. Um, and so M is just an A module. But then this is localization of M at the multiplicative set of functions not vanishing outside of F. There's some F. And then, of course, MP is the localization of this at the function P prime ideal, right? And so this is at or functions at the point P at functions not vanishing on the prime ideal P. And then I guess it's worth stating that MP is the localization of M at P. And what this looks like is basically the localization at functions not vanishing on V of P. And so we can see pretty clearly that this canonical isomorphism definitely exists because these two criteria are exactly the same.
Yeah.
And so yeah. What's the next thing we need to do? Oh, I guess there is in particular, the stalk of O spec A at the point P is the local ring AP. And I mean, this is just kind of how we constructed the module structure. Like if we think back to yesterday, we said that like each MF is an AF module, but then it makes sense that the local ring is going to be AP if you have a prime ideal of things generated by F, like so. So I think that this makes a lot of sense. Do you feel that way? Do I need to go more in depth here?
No, that makes sense.
Okay. Um, yeah. So 4.1.f is this business about the first thing in our sequence um, here. And it's about showing, it phrases it slightly differently from the math stack exchange proof we went through yesterday. But it's basically the same idea. Basically, it must be an injection.
Yeah.
And so we did 4.1.f A. We could have also done it by showing that since sections of a sheaf are determined by germs, then the germs are injective. Um, and so a corollary of this injectivity, so I'll go ahead and just write out the theorem, but we won't prove it because we proved it yesterday. Um, so M 2P spec A MP is injective, and then the corollary is that M is the zero module if and only if its prime ideals are all zero. Oh, sorry, it's localizations at. Um, is that clear how the corollary follows from the theorem directly?
Yeah.
Okay. Um, yeah. Okay, so then 4.1.g. So we want to describe a bijection between maps of A modules M to N and maps of O spec modules M N. Okay. I want to state this again as a theorem. So there exists a bijection between maps of A modules M and N and maps of structure sheaf modules. And namely, we're going to call this phi, and it's going to be from HOM MN to HOM. And I wanted, before I write anything down next, I want to check something on the great internet, because I'm pretty sure this involves something with tensor products, because this is how they phrase things with extinctor. I'm like almost certain that this is a tensor product thing. Um, oh yeah, okay. I'm gonna clarify which HOM we're working in. Um, and so, okay. Let's start with, I'm gonna leave this unnamed for now. So let's say we have phi from M to N. Um, then um, we want the associated morphism in the second HOM um, to be on open sets. And so then what we're going to say is that phi tilde of df is from the localization at f to localization at f, sending um, and I'm not exactly sure what the deal with k. I think it's k in greater than 0. Whoever wrote this on Math Stack Exchange did not help very much. Um, hold on. Let me look in the comments. Okay, it is k greater than or equal to 0, and it's because the localization runs through 0. So yeah, that makes sense. Yeah. And I guess this comes from f to the L times f2 km minus for some L and k prime. Um, so now that we have both maps defined, we want to send no, is this uniquely associated? Like if you have like so let M in M, then the first 5M is in N, but then this maps down by, we're gonna call this, we'll use psi. Maps down to M over F to the K goes to 5M over F to the K. I don't know. Does this seem like a reasonable construction?
Yeah.
Cool. No, I messed up a page of the book. Conclusion of this exercise is really that A modules are a full subcategory of structure sheaf modules. I don't know if anybody actually calls them structure sheaf modules. Let me check that. Okay. They kind of call it that. All right, I'm gonna start throwing that word or that term around a little bit less then. If it's not like a, I think it makes a lot more sense to call mod like OSPEC A mod structure sheaf module because that's what it is. But I don't know. Unless I'm horribly misunderstanding something.
Should email Vakil.
Yeah. I want to wait to have a good first question, you know what I mean?
Yeah.
Okay. So, we're going to define the support of an element of a module to be the set of points in spec A such that the localization by those points is non-zero. Which is the support of M considered as a section. And I guess this is this is a bit of a recursive definition, but like this is a section of the sheaf and it happens to correspond to its support.
Okay.
And then a follow-up definition. Oh, and it's a section of the spec A module.
Yeah.
right? So similarly, the support of the actual module um, is the support of the spec A module, or the O-spec A module, which is the sets of P in spec A, such that the localization of the A module at P is non-zero in spec A. It's worth noting that these are the same module, right? These are A modules.
Yeah.
Whereas this is O spec A. Okay. So there's a section called recurring counterexamples. I'm a little confused, but okay. The example of two planes meeting at a point will appear many times as an example or a counterexample. It's important to have such examples at the back of your mind as boundary markers, reminding you of what is reasonable and what to watch out for when you hear a new statement. The appearances of the following are listed in the index under recurring counterexamples, so you can see how they come up, how often they come up, and where. We do not have the language to understand many of these yet, but you can come back to this list later. So two planes meeting at a point, affine space minus the origin and its inclusion in affine space. Affine space with doubled origin, the cone over a specific quadric surface, an embedded point on a line, x squared equals 0 in the projective plane, infinite disjoint unions of schemes, the morphism from the spectrum of the closure of Q to spec Q, which I'm pretty sure is isomorphic to the real numbers. I think that's arithmetic genus of, yeah, anyway. We're pretty quickly hitting things that we don't know. So anyway, we'll just keep track of these. Okay. On to 4.2. We're making pretty good time. The price of metaphor is eternal vigilance. A. Rosenbluth. Interesting. Point 2. So in section 3, we discussed how to visualize the underlying set of schemes, adding in generic points to our previous intuition of classical or closed points. Our later discussion of the Zariski topology fit well with that picture. In our definition of the affine scheme, spec A and its structure sheaf, we have the additional information of nilpotents which are invisible on the level of points. So now we figure out how to picture them. We will then readily be able to glue them together to picture schemes in general once we've made the appropriate definitions. As we are building intuition in this section, we cannot be rigorous or precise. So, great. So as motivation, we have inclusion, reversing bijections. Inclusion, reversing between maximal ideals of A, closed points of spec A, we have prime ideals of A, and then we have irreducible closed subsets of spec A. And then we have radical ideals. And then we have closed subsets of spec A. If we take the things on the right as pictures, our goal is to figure out how to picture ideals that are not radical. So, ideals of A. Dude, having met him in person, I can picture him talking through this stuff, and it's
Yeah.
he has a great sense of humor, and it comes through in the writing. We will later. Wow, we will later fill this in rigorously in a different way with the notion of a closed subscheme, and I'm going to write this in closed subscheme. That actually worked pretty well.
Huh.
But we're not going to worry about that now. The scheme, theoretic version of closed subsets, but our goal now is to create a picture. As a motivation, when we see the expression spec C over X mod the ideal X times X minus 1 times X minus 2. We immediately interpret it as a closed subset of affine one space. Namely, the set 0, 1, 2. In particular, the map from C over X to this quotient space can be interpreted as taking a function on affine line, restrict it to 0, 1, 2. It's worth mentioning, I need to state a theorem that I haven't used in a while. So let me look it up. It's called the Chinese remainder theorem.
Go.
And so let me go ahead and just state, and this is how we get the decomposition. So theorem, Chinese remainder. And I'm going to state it algebraically first, and then with spec A. So I'm going to do this in two different colors. So let A be a commutative ring, and let I1 through IN be ideals of A with II plus IJ equal to A for all I not equal to J. This specific thing is called pairwise comaximal ideals. Then this is the actual Chinese remainder theorem. As rings, A mod the intersection I equals 1 to n of I is isomorphic to the product I equals 1 to n of A mod I as rings. Okay, and then geometrically, what this looks like is spec of A mod the intersection I equals 1 to n of I is isomorphic to to the disjoint union of spec A mod II. Where have we seen this before? Well, we've seen this with the fundamental theorem of finite abelian groups.
Yep.
So, for example, when we decompose Z25 into C5 product C5, what we're really saying is that Z is the ring mod the intersection I equals 1 to 2 of 5Z intersect 5Z is isomorphic to C mod 5Z Z mod 5Z. Right, so we've used it before, we've just called it something different. But it's useful for, and we're going to use it increasingly, like I was flipping through the book earlier this week in the car on the drive in Florida, just kind of scouting out like where we're going, what I should keep in mind, like all kinds of stuff. We're going to use this theorem increasingly just to get like meaningful interpretations of things. So
yeah, when you mentioned it, I remembered seeing it on a Math Stack Exchange over the summer.
Yeah. Yeah, it's very important to cryptography, especially.
Yeah.
But yeah, so basically, taking it back over here, when we're looking at our polynomial rings, we can take this thing over to, each individual point, right? So really, it's the power set of this.
Yeah.
Anyway, so this will guide us on how to visualize a non-radical ideal. The simplest example is to consider spec C over X mod X squared as a subset of affine one space. It is just the origin because it only vanishes at 0. Which we're used to thinking as spec C over X mod the ideal generated by X.
Yeah.
which corresponds to x, not x squared. Um, to enrich this, we want to picture it in terms of the information the quotient remembers. So the image of a polynomial f of x is the information of its value at 0 and its derivative. So we can thus picture this as being the point plus a little bit more, a little bit of infinitesimal fuzz on the point. And so now is where I need to draw a picture, which is never a good thing. Um, so if we have this point, spec c over x mod, ideal generated by x cubed, spec c over x mod x squared and then spec c over x mod x. Then this is just a point, and then this is the fuzz.
That makes
Right.
sense.
Um, so the sequence of restrictions should be interpreted as nested pictures that look like c over x to c over x mod x squared. Oh, and these are surjections. To c over x mod x, which sends f of x to 0, factoring through 0. Or sorry, not to 0, f of 0. So similarly, modding out by x cubed remembers even more information, the second derivative as well. So thus we can picture this as the point 0 with even more fuzz. And so we can also think of the fuzz as differential information. Right? So remember we said a while ago with the no radical, it keeps track of differential information. This is where that will show back up eventually. So most subtleties arise in 2 dimensions. So take, for example, c over x comma y mod x comma y squared as an ideal. Well, this is sandwiched in between 2 rings that we know pretty well. I'm just going to highlight this so that we know it's the thing we care about. We have c over x comma y. And then we have c over x comma y mod xy. And this sends f of xy to f of 0 comma 0. So again, the quotient by xy squared remembers the first derivative in all directions. We picture this as the fuzz around the point in the shape of a circle. No direction is privileged. Similarly, xy cubed ideal remembers the second derivative in all directions, bigger circular fuzz. So now consider the ideal x squared y. What it remembers is the derivative in the x direction. And then its value at 0, 0. But we only should picture the fuzz as going in the x direction. And so this gives us a handle on picturing more things of this sort, but now it becomes more of an art than a science. For example, modding out by x squared y squared can be pictured as a fuzzy square around the origin. And then this square is circumscribed by the circular fuzz of... Okay, I'm going to write this down. This is kind of cool. So spec c over xy. I'm just going to copy that because I'm going to be using that a lot in a second. Mod x squared y squared is a fuzz square around 0, 0, which is circumscribed in as a circle. That's kind of cool. One feature of this example is that given two ideals of a ring, your fuzzy picture of spec A mod the ideal generated by I and J should be the intersection of your picture of spec A mod I and spec A mod J in spec A. And this makes sense from the Chinese remainder theorem. So one final example that will motivate us is this mod y squared xy. So knowing f of it, I'm going to call this z. We don't use z for anything. Knowing f of x and z is knowing f of x in... Oh, wait, sorry. F of x comma y. On the x-axis, and first order differential info around the origin. I'm a little confused. It seems like it would be. Hmm. Who knows? Okay. Um, I don't know. Does what I just wrote down make sense to you?
Yes.
Okay. Um, hmm. So this can be pictured as. Hold on. Fuzzy ball. Yeah, that's good enough. Um, that's 0, 0. Um, yeah, our pictures capture useful information that you already have some intuition for. For example, consider the intersection of the parabola y equals x squared and the x-axis in the xy plane. You already have a sense that the intersection has multiplicity 2. In terms of this visualization, we interpret this as intersecting in spec cxy as basically exactly what you would want it to be. Um, so we'll write it out. It has something useful there. Spec spec c y mod y minus x squared y, which is spec c xy mod y comma x, which we interpret as the parabola and line um, which we interpret as the fact that the parabola and line not just meet. I think we just found a grammar error. Do you see this on page 94?
Hang on.
It's right above 4.2.1.
The which we interpret as the fact that parabola and line.
Yeah, not just meet. I think he meant to say do not just meet.
Yeah, I think that's it.
Okay. We should let him know. Add this to the list.
Yeah.
Page 94, above 4.2.1. Do not just meet. Okay. We'll save this all for when we have an actually good question. We could be like, hey, here's our
Yeah.
legitimate question. And also, by the way, um, anyway, yeah, multiplicity 2 part is in the direction of the x-axis. So parabola and line meet with multiplicity 2 in the direction of the x-axis. Right, so it's multiplicity 1 in the direction of the y-axis, and then it's multiplicity 2 in the direction of the x-axis. So we will later make the location of the fuzz more precise when we discuss associated points. We will see that in reasonable circumstances, the fuzz is concentrated on closed subsets. It is often said that geometry is the art of reasoning well from badly made figures. However, these figures, if they are not to deceive us, must satisfy certain conditions. The proportions may be grossly altered, but the relative positions of the different parts must not be upset. And the picture for the above is if you have a parabola intersect the x-axis, what you get is just a thicker x-axis around 0, which is a non-reduced scheme with fuzz in the x direction. Yeah. I'm going to say let's take a 5-minute break and then come back and start on the definition of schemes, go till 9:30, and then take a break for half an hour and then come back at 10.
Okay.
Cool. All right. Be right back. Be back at 8:53 or so.
Okay.
All right, I'm back.
All right, what's up?
Um, Let me just get settled. Um, cool. All right, so now we can talk about the definition of schemes. So, 4.3, schemes, finally. All right, first we're going to define an isomorphism of ring spaces. So, an iso of ring spaces, x, nope, ox, 2y, oy is 1, a homeomorphism pi from x to y, and 2, an isomorphism of sheaves. Ox to oy, considered to be on the same space via pi. More precisely, this is obtained by pi of y. That, nope, nope. Pi of x. Or pi inverse of y to ox. Okay. In other words, we have a correspondence of sets, topologies, and structure sheaves. Every isomorphism of ring spaces, alpha from x to y, clearly admits an inverse. And now we can define an affine scheme. So, an affine scheme is a ring space which is isomorphic to spec A and our associated structure sheaf on spec A with, some A. A general scheme x ox is a ring space such that for every x in X, there exists an open neighborhood U such that U OX restricted to U is an affine scheme. The topology on a scheme is Zariski. We often just use X to denote the scheme X, OX. Okay, an isomorphism of schemes. Harry Potter and the never-ending definition. Oh my goodness. Um, is an isomorphism of ringed spaces. If U is an open subset of X, then the global sections functor sending that open subset to its section in its structure sheaf is the set of functions on U, which generalizes the entire definition of an affine scheme. Wow. Yeah, Harry Potter and the definition that would not end. Okay. I just need to look ahead a little bit to get a roadmap for today. Figure out where I want to stop, where I want to pick up. Hey, we're about to hit page 100.
About to hit what?
About to hit page 100.
Oh, wow.
In my heart of hearts, I would love to get through 4.5 today. I would love to get up to page 8. I think that is actually very ambitious, but if we could finish chapter 4 today, I would be incredibly happy. So, okay. With that said, let's go through this. I think I'll pause. I'll try and get us up to 4.4 in the next half hour. Never mind. There's an enlightening exercise which can be strangely confusing. Oh God. Okay, so I'm going to start with the remark. So remark, from the definition of the structure sheaf on an affine scheme, several things are clear. So if X ox is an affine scheme, we can recover its ring. Ring A such that spec A is equal to X. This is accomplished by letting X equal that doesn't vanish on 1, so that the global sections functor on X to ox is equal to global sections as the doesn't vanish on 1 is just spec A. And then this equals A. You can verify that we get more and can recognize X as the scheme spec A. We get an isomorphism pi from, oh God, spec gamma X ox. Oh, spec gamma X ox. 2x ox. I'm gonna put this in a different color because that just needs to be the different color. Yeah, purple seems fitting. For example, if M is a maximal ideal of the global section functor of the scheme, then the set of pi of M is equal to the vanishing of the maximal ideal. Yeah, the following exercise will make these ideas rigorous. They're subtler than they first appear. Give me just 1 second. I need to send a text. Right. So, caution, it is not part of the definition that the overlap of two affine open subsets is also affine. Although this is true in most cases of interest, it is not true in generality. So, theorem, there exists a bijection between the isomorphisms spec A to spec A prime and then A prime to A. What the heck? Other ring. And then the hardest part is to show that if an isomorphism pi from spec, wait. A bijection between the isomorphisms of ring spaces and the ring isomorphisms. Okay. Hint, consider pi from spec A to spec A prime induces an isomorphism pi sharp from A prime to A, which in turn induces an isomorphism rho from spec A to spec A prime. Oh, hint, if. Then pi equals rho. And I'm just gonna throw this out there, having looked ahead. Pi sharp and I believe rho show up later, so it's kind of important to keep track of these. These show up later. Um, Wait. Okay, and then so our plan for proof is that pi equals rho on points. And then pi equals rho as topological spaces. Feel free to use insights from later in this section, but be careful to avoid circular arguments. Even struggling with this exercise and failing will be helpful. Vakil, what? um, okay. So that's just wonderful. Okay. So assuming that these morphisms exist, then if we pick, so these are ring space, so hold on. Ring space. This is a ring. This is a ringed space. And so what we want to do is we want to show there exists a bijection. And I mean, okay, what we're doing, I don't know what we're doing. Like, okay, clearly there's something going on with the Ham functor here. Because we have like this inclusion reversing thing going on. Garrett, do you have any ideas?
Not a clue.
Okay.
Um,
So on points, we maybe want to just take like let x and spec A. Um, be a point correspond to pi of x in spec A prime. Then pi sharp induced by pi has all of the functions in A prime vanishing. Has, we'll call it I equal functions vanishing on pi of x as pi sharp of I. Oh, and by the way, this is just v of pi of x. In, oh, and this is in A prime. And this is in A. And then if we take this back, so far we have x to pi of x to I to pi sharp of I. And then we want to send this down back to x and show that this goes to rho of x and that this is the same thing. So sending pi sharp of I back to prime ideals vanishing on it, then let, and really this isn't x, this is, let's call it j, let's call it y. Let y be the ideal. Ooh, I shouldn't have used I. Oh, I should not have used I. Let's use z, because that's pretty innocuous. Alright, so then I of z is the ideal generated by z. Equals functions vanishing on, oh, and it's not of z, it's of pi sharp of z. And then And then this is an ideal. And at this point, it's in spec A. Or it's an ideal of A living in spec A. And then rho y is equal to rho of I of pi sharp c. And I'm just gonna break it down one stage further. No, that's okay. No, a v of pi of x. Okay. And we want to claim that
Well, there's Harry Potter and the never-ending parentheses.
yeah, claim y equals I of pi sharp of v of pi of x is equal to x. And rho of y is equal to pi of x. And I'm going to say that my proof sketch for this claim is that each of these operations, or of each of these morphisms and functors, are invertible and co/contravariant in the necessary spots. And I think that that does actually work, right?
Yeah.
Because what we're saying is that we can undo rho, then this is I. Let me use a color I haven't used in the diagram yet. Let me use, okay, rho I pi sharp v pi. And so basically, you can take the contravariant inverse functor of I, which is v, um, right? So this is like the I functor, this is the v functor. We know that they're inclusion reversing. And we can get kind of back like that. Right? And they're contravariant inclusion reversing. And so that's gonna do it for us. Okay, so I'm gonna go ahead and say we understand this on points. But then on topological spaces, what we need to have happen is we need to be able to take any open neighborhood um, and map it with pi. Um, And I think that the same argument follows. I think that there's just some machinery going on. Oh Lord. um, I think that there's just some machinery going on in terms of dealing with the topology of spec A and the topology of ring spaces, but it breaks down to the same idea of co and contravariance and inclusion reversing in the necessary spots.
Yeah.
So I'm pretty happy with this. Um, yeah. So I'm gonna put a dot 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 box. You should probably work through the topology part on your own.
Yeah.
That's actually the easier part. And then taking any open subset as a composition of distinguished base elements. Um, it shows it on the level of structure sheaves, and so then it just kind of works out.
Yeah.
Right. So my hint slash answer is take U, open in spec A, make a base D of F, and then run through the diagram. And I guess really this is df is equal to u. So anyway, more generally, um, given f and a, then the global sections functor of the does not vanish set is isomorphic to the localization of a f. Under the natural inclusion of sets, spec AF to spec A. Oh wait. Under the natural inclusion of sets, the Zariski topology on spec A restricts to Zariski on spec AF. And structure sheaves restrict O spec AF, or no, O spec A to O spec AF. And I think this just kind of works. And this is a result of the following theorem that F and A by identifying D of F in spec A with spec AF, there exists an isomorphism of ring spaces. D of F, O spec A restricted to D of F.
But
X. 2 spec AF O spec AF. And this is pretty easy to show. This is a result of this theorem.
Yep.
And then kind of as a resulting theorem, if X is a scheme and U is any open subset, U OX restricted to U is a scheme. And really what we're thinking about here, like analogously to Hartshorne, is this is a quasi-projective variety.
Okay.
So it's 9:30. I think we can either finish 4.3 right now and just take a 30-minute break whenever we finish 4.3, or we can stop now, take the planned 30-minute break, and come back.
I'm gonna take care of a few things because I planned for that 30-minute break at 9:30. Could we just
All
grab
right.
a nap?
Yep. Then I'll go ahead and stop the recording, and we'll come back in a little bit.
All right.
All right.